Hey everybody, so this is the start of your new unit on exponential functions. Sorry, it took me a second here to get it going. All right, so we're going to start really quickly by reviewing linear functions because that's what we have spent pretty much half the semester looking at, even though it was systems of linear functions and systems of linear inequalities. They were all linear. Okay, so for example, if I have the initial sign up fee for a new gym is $40 and the monthly fee for the gym is $20, what would that look like? Okay, so if I've been to the gym 0 months thus far, but I signed up for my gym membership, then I would be paying the gym $40. Okay, I've signed up, but I haven't received my first month's bill. Okay, so if I go to the gym for 1 month, it's $20 per month plus my $40 membership fee. So you've got $60. If I go for 2 months, it's $20 per month plus my $40 membership fee. So that's a total of $80. $20 for 3 months plus my initial fee of 40. So I've got 100, and then I'm sure you can make a prediction based on your pattern here. You're adding 20 every single time. Okay. And so your next one, I must have add 20 so as not to break that pattern. Okay, and this right here is what makes it a linear function, because linear functions subtract or add by the same amount every single time. Okay, so when I put it on the graph, let's say my y values are in tens so that I can make it fit on here. And then these are my x values, they can stay as ones. So 0, 40, 160, 280, 3, 100, and then it would go off the graph. But it is a very straight line. My rate of change remains the same for every increase of one value. So that would result in this function in slope-intercept form. So y equals mx plus b. What is my rate of change or slope? It's $20 per month. And what is my initial fee or y-intercept? That's how much I'm being charged to get into the gym initially. Okay, so that brings us to exponential functions. How do they differ from our linear functions? So why don't we start off with a real world example or a word problem. So one bacterium is placed in a petri dish. The number of bacteria in the dish doubles every hour. All right, so what does that pattern look like numerically? Well, hour 0, I have placed one bacterium in the dish. There is one singular cell in that petri dish. Okay, the number of bacteria doubles every hour. So the next hour I would have 2 bacteria. The next hour I would have 4, and then 8, and then 16. So with every increase of 1 hour, I am multiplying by 2 every single time. Okay, and what does that look like on the graph? Well, 0, 1, 1, 2, 2, 4, 4, 8, and then my next value goes off the graph, okay? Now, what does that look like in an equation? It looks like this, okay? So one thing on this slide, 2 things I want you to notice. One, we're multiplying by 2 every time. So an exponential function is going to have a pattern of multiplication on your XY chart. And then we've got a curved graph, right? It's not linear. For every increase of one x value, my rate of change is increasing from one to the next. Okay, it's not remaining constant. So let's break down that equation. You've got an initial value A, and that's where it intersects your graph on the y-axis. So this is also your y-intercept. Okay, B is your rate, and that's what you're multiplying by every time. And then x and y are just any ordered pair. So in our previous example with the bacteria, you had y equals 2 to the power of x. Okay, so I could rewrite that as y equals 1 times 2 to the power of x. So what was my initial value? 1. I started with 1 bacterium in the dish, and then it was physically where the line crossed the y-axis. And then what was my pattern on the XY chart? I was multiplying by 2 every single time. It was doubling the amount of bacteria in the Petri dish every time. Okay, so exponentials, they're graphs and how the initial value and rate of change affect those graphs. Okay, so just focusing on the graphs of exponential functions for today and breaking down that equation and using it. Okay, so I'm sticking with this as my kind of basic function to compare every single time. So if I have an x value of -1, what is my y value? So I would substitute -1 into my equation. So I have 2 times 2 to the power of -1. And if you'll reflect back on that exponent laws video, anything to a negative exponent is a fraction. So 2 times a half is 1. And then 2 times 2 to the power of 0. Any number raised to the power of 0 is 1. So what is 2 times 1? 2. And then substituting 1 for my x value, I get 4. And then substituting 2 for my x value, I get 8. So notice it's doubling from one row to the next because my rate is 2. Okay, so when I put that on the graph, I have -1, 1, 0, 2, 1, 4, 2, 8. And it's gonna go up to the right like this, not the best curve. And then it's gonna go down in this direction. Okay, and I'm gonna revisit that in just a second. So let's take a look what happens here when I switch my B. Notice here, my B is a fraction, 1/2, right? I'm gonna do this one in blue. So I've got 2 times 2 to the power, that should be half. So 2 times a half to the power of -1. Okay, 1/2 to the power of -1 is actually 2. So that is 4. And if you need to, you could type that in your calculator for confirmation. So 2, and then you've got 1/2 to the power of 0. Any number to the power of 0 is 1. So 2 times 1 is 2. And keep on with your substitution here. So 1/2 to the power of 1 is a half. 2 times a half is 1. And then 2 times a half to the power of 2. What happens when I've got my fraction raised to the power of 2? Just 2 times a fourth. Okay, so that's a half. So what you should notice this time is that rather than doubling, I am multiplying by a half every single time from one row to the next. 1/2 of 4 is 2. 1/2 of 2 is 1. And then 1/2 of 1 is a half. So when I put this function on the graph, I am going to have, let's see here, -1, 4, 0, 2, and 1, 1, 2, 1/2. And so what I want you to notice with this graph is that it gets closer and closer to 0, but it never actually touches 0. And that's super important. Your graph, although it may look like it touches 0, isn't going to touch 0. And why is that the case? You might want to jot that down or commit that to memory. Never touches 0, or in other words, it approaches 0. Why is this the case? Because what you need to remember is negative exponents do not mean negative answers. They mean fractions. So as I am raising 2 to negative numbers, so let's say it's 2 to the -4, my answer is going to be 2 times 1 over 2 to the 4th power. It's not going to be a negative answer. Okay, let me finish that one out. So I would have 2 to the 4th, 1/16. 2 times 1/16. 2 over 16, 1/8. And so those fractions are just going to get smaller and smaller and smaller, but they're never actually going to touch 0. Okay? And what else do you notice? How did the changing of my rate from a whole number to a fraction change the graph? Okay? So we went from a graph that looked like this, and that it's not very steep, but you get the general idea, to a graph that looks like this. Horrible sketch, but you get the idea. So when b is greater than 1, it's exponential growth. Okay, so that's this graph right here. And then when b is a fraction, it's going to be called exponential decay, and that corresponds to this graph. So you have one function that's increasing exponentially up and up and up, and then another function that is decreasing down, down, down. And I'm going to write those equations back in here. So you had y equals 2 and then times 2 to the x power versus y equals 2 and then a half to the power of x. Okay, and we're comparing the b values here. Okay, so what happens when the initial value is changed? So remember back in our original function, a, b, this is your initial value. How does that impact the graph? So again, this was my standard one that I'm always going to use to compare on these slides. So you're going to start with a 1. Your 0 value is 2, 4, and then 8. And that was on a previous slide. So for this next function, well, let me go ahead and put that on the graph. So -1, 1, 0, 2, 1, 4, 2, 8. And again, this is the graph I'm kind of using to compare every single time. Oof, let me do that again. That's horrible. Okay, so -1, 1, 0, 2, 1, 4, 2, 8. And let me try that one more time. All right. So that is our standard graph. And then we're going to compare it to a negative a value. So we're looking at our a values. I would have -2 times 2 to the power of -1. So that results in -2 times 1/2. Okay, well that's -1. So -2 times 2 to the power of 0, -2 times 1, -2. And then -2 times 2 to the power of 1 is -4, sorry. And then -2 to the power, okay, to -8. Okay, so what you should notice now is we're multiplying by 2 every time still. But we've got negative numbers that we're dealing with. So our rate is the same in both of these functions, but I have a different initial value. And how does that impact my graph? So -1, -1, 0, -2, 1, -4, 2, -8. So what's going to happen is your graph is going to flip upside down because of that new a value being negative. Okay. And now we're going to take a look at our rates are the same. What happens if a is now a fraction? Does that have a tremendous effect on my graph? Now remember, this is my kind of standard function, and my initial value is 2, and it's doubling every time. So these values were from previous slides. And let's go ahead and put our standard graph on there. So hopefully I will do a better job of graphing it right off the bat. That's a little bit better. Not great, but better. And then we're going to see what happens when I make a fraction. So I'm going to have 1/2 times 2 to the power of -1. 1/2 times 2 to the power of 0. 1/2 times 2 to the power of 1. And 1/2 times 2 to the power of 2. And in some ways, it might be easier working from bottom to top here. So 2 squared is 4. What is 1/2 times 4? 2. 1/2 of 2 is 1. And then 1/2 of 1 is 1/2. So what's happening is I'm going to end up with 1/2 times 1/2, or 1/4. So I'm still doubling every time. It's just that I've started in fractions. Okay, so -1, 1/4, 0, 1/2, 1, 1, 2, 2, and then 3 would probably be 4, and 4 would probably be 8. So how does a being a fraction really affect the graph of the exponential? All it's done is taken my original graph and slid it down. So if I increased a to something like 4 and kept my rate the same, what would happen is the graph would just move up to 4, but remain the same slantedness. And maybe I should have put that in a different color. So in summary, what's happening is my a value is affecting the y-intercept of my graph. So again, when I increase my a, it's just going to move it up the y-axis, but remain the same slantedness. So let's summarize that. How does the value of a impact the graph of an exponential function? So in general, it is your y-intercept. It is where your graph is intersecting the y-axis on the coordinate plane. And I'm not sure why it keeps doing that little weird. Okay. So here is your A, where it crosses the y-axis, okay? When A is negative, it's going to flip it or reflect it, if you want to use better math vocabulary, over the x-axis, okay? So here's our standard equation or the one that we've been using to compare. And if we make that A negative, it flips it over the x-axis. Okay, and then if any other value of A is just going to move it up or down the graph. So if you had y equals a half to the power of x, it's just going to move it lower on the graph, your exponential. Okay, so that was just a quick introduction to your exponential functions, and I'm just going to give you some practice with their graphs, and then we'll get into kind of the deeper ins and outs of exponentials later.